Hey, so let's ask ourselves, how can we solve equations where the exponents actually are the unknowns? So let's start figuring out how to solve exponential equations. We saw some simple cases of this a while back where the idea was if you can get the same base, then you could just set the exponents equal to each other. But how do you do that when in fact things get a little bit ugly? Well, then the logarithm actually comes to our rescue. So let's start off with a very simple example just to get us sort of in the right mood. So this would be 3/4 to the x, and suppose that equals 16 over 9. Okay, and now what I want to do is figure out what value of x would make this thing actually hold. Well, there's a variety of ways of thinking about it. Let me actually share a couple with you. One is to say, okay, I'm going to try to get this thing to be the same base as this. So you can see it's looking actually not bad. I can sort of make this thing without too much effort into a 4/3 by just squaring. So that was pretty easy. It looks so close to this. I actually want a 3/4. Well, how do I make that a 3/4? I just take 4/3 and flip it twice. 4/3, 3/4, 4/3. So flipping it twice means flip it here and then put a negative sign up there. Right? I flipped it here, whoop, but then the negative flips it again. So it just comes right back to 4/3. Doesn't change the value. But now I'm in great shape because since the bases are the same, that means the exponents must be the same. So x must equal -2. Pretty easy. So when I can actually massage one side to match up perfectly with the base of another, I'm in hog heaven. But consider the following more exotic example. Suppose I take 3, raise it to the x minus 2, and I want that to equal 4 raised to the 2x plus 1. And I want to find out the value for x, which actually makes this true. Well, there's no way for me to take the 3 and make it into a 4 to a power, or a 4 and make it into a 3 power in some sort of easy, straightforward way. So what would I do? Well, here's the key idea. The key idea is to go back to these formulas, and in particular this one. Let's think about this formula. This says if I have log of something to a power, that power can be rewritten as just a coefficient. I can bring a power out in front. Now, if you notice, with an exponential equation like this, the unfortunate thing, the thing that I hate, is that the unknowns are in the exponent. I want unknowns to be on ground level so I can do all the arithmetic that I already know about arithmetic to solve. But the problem is I don't know much arithmetic about how to deal with things when they're in the exponent. So I want to bring them down. I want to get down. Get down. Now how do you get down? Well, if I took the logarithm of both sides, then I could use that property to pull the things out in front. Then exponents become coefficients. So whenever you want an exponent to become a coefficient, whenever you want an unknown that's in the exponent to be able to be usable, just take logs of both sides. You see, if two things are equal, their logs will be equal. Now you can take any log you want. You can take log base 7, you could take log base 3, log base 4, log base e, or just log base 10. I'll just take log base 10 because maybe at the end of the day I might want to use my calculator to actually figure out what the values are. So let's log both sides. So if you log both sides, do some log rolling here, we have log of 3 to the x minus 2, and that will equal log of 4 to the 2x plus 1. Okay, well now I can use this fantastic property of logarithms, which is crucial, that exponents can be written out in front as coefficients, and that saves us. Because now I can write this as x minus 2 times log of 3. Log of 3 is just some number, equals 2x plus 1 times log of 4. Notice these parentheses, by the way. It's because this log has to hit both terms. This log has to hit both terms. I have to distribute. Don't make the cardinal standard classic mistake of not distributing here. If I do distribute, and remember, log 3 and log 4, they're just some numbers. I don't know exactly what they are numerically. I can use a calculator and figure them out, not a problem, but they are numbers. So if I distribute, I see log 3 times x minus 2 log 3 equals 2 log 4 times x plus log 4. You notice I put the little parentheses around here? You know why? If I didn't put the parentheses around there, you may have thought that maybe, imagine this without parentheses. In fact, I'll just show it to you without parentheses. If I write it without parentheses, it would look like this. And you may have thought maybe it's log of that whole thing. And it's not log of this whole thing. It's just log of 4, but I multiply the whole thing by x. So the x is way on the outside. The x is not part of the log. You see the x is way over here, times log 4. OK, well, now what can I do here? I want to solve for x. So I'll just bring all the x's over to this side. And if I do that, I see log 3 times x. And then I have a minus. I subtract this, so I have minus 2 log 4x. And what does that equal? Well, I'll bring the constant stuff to this side. So I'll see a 2 log 3 plus log 4. So I want to solve this. I can actually simplify this quite a bit. Let's take a look at how we can actually simplify this if we wanted to. All right, here we go. So the first thing I do is notice I can factor out the x here. And so if I do that, I've got a log 3. But actually, I'm going to do a little simplification at the same time, because notice this 2 can be brought upstairs to this exponent on a 4, and I could write that as minus, there's the minus, log of 4 squared, which is 16 x. So I factored out the x and also did that step at the same time. Now watch this big step I'm going to do right here. The big step I'm going to do right here is, first of all, take this 2 and pull it up on top, so it becomes a log 3 squared, which is log 9. And then I have a plus log 4. Now I can actually combine a lot of these guys. I see the difference of logs. Remember, that's the log of the quotient. So I could write this as log of 3 divided by 16, x, and that will equal log of, and if I'm adding logs, I can multiply them. So in fact, this is just 9 times 4, which is 36. If I divide through by this thing, that's a number, I get what x equals. So x, it turns out, equals log 36 divided by log of 3 over 16. So that's the answer. What is the x that satisfies this? It turns out the answer is some exotic x. It's that. What does that equal numerically? Well, you can just pop on a calculator and take a look at it if you want. Log of 36 divided by log, whoops, hold on a second. I seem to be having some mechanical difficulty here. Let's see, mechanical difficulty. Here we go. Log of 36 divided by log of 3 divided by 16 equals minus 2.1407 stuff. So basically, the x that works here and satisfies this is equal to minus 2.1407 stuff. You can see it's sort of a weird answer, but that's the exact answer to make these all equal. OK, wow, that took a long time, didn't it? Whew, a lot of work, but not that hard, just a lot of work. All right, let's try one last one here. Suppose I want to solve 2 to the 2x minus 3 equals 5 to the minus x minus 1. I want to find the value of x. I want to find the value of x which makes this thing hold. So what do I do? Well, what I do is I see that there's no way of making a 5 a 2 or 2 a 5 an easy way, so I'll just take logs of both sides. If I take logs of both sides, so log of 2 to the 2x minus 3 equals log of 5 to the minus x minus 1, then I can use laws of exponents to pull this out in front, pull that out in front. And using the log stuff, I see the quantity 2x minus 3 times log of 2 equals the quantity minus x minus 1 log of 5. Well, now all the x's are down below. They're not in the exponents anymore. Of course, there's a price you pay for that. I now have logs in the picture. But OK, that's OK. They're just logs of numbers. So what do I care about? I can distribute these logs, and I'd see, let's see, 2 log 2 times x minus 3 log 2 equals, let's see, here I'd see a minus log 5x, and then here I'd see a minus log 5. What can I do now? Well, I can bring this stuff with x's over to this side, so it becomes a plus. This 2 out in front, I can pull that up and make it a log 2 squared. So I'll just write log to the 4, log of 4, because that's 2 squared. I bring this over, it becomes a plus log 5, and that's all times x. I factored out the x. And then if I bring this minus 3 log 2 over to this side, what does it look like? It becomes a plus 3 log 2, which is just a fancy way of saying log 8. Because if I take that 3 and put it up as an exponent, it's 2 cubed. And 2 cubed is 8. But I still have that minus log 5. Well, log 4 plus log 5, remember the laws of logs, that's just log of the product. So that's just log of 20x. And that equals log of, and the difference of logs is just the log of the quotient. So log of 8 over 5. Great. So now I can actually solve for x exactly. I'll do that right here. And I see that x equals log of 8 over 5, all divided by log of 20. Okay, do you see all the little steps there? There are a whole bunch of little teeny steps, like bringing the 2 up here as an exponent becomes a log 4. Bringing the 3 up here as an exponent becomes a log 8, and so on. But now there's the answer, and you can actually compute that away if you wanted to. Let's see if we can do that really fast. Log of 8 divided by 5, and then I take that answer and divide it by log of 20. So numerically, this equals, x equals 0.15689 stuff. So the x value that makes this whole turns out to be sort of an exotic number. It's 0.15689 stuff. The method was just to take logs, and the logs have the feature that it turns these exponents into coefficients. Really powerful with a small price to pay, just some logs of numbers which calculators can easily spit out to you. Try these, have some fun with them.